In the previous talk, we have seen like what are graph signals, what are the architectures in a way we can process this data, and also some applications. But so far, the graph was known. So we suppose that the graph, let's say, was given, and then we wanted to process the data on top of this graph. But there are many scenarios in which we don't have actually the structure of the network. For instance, in neuroscience, like you can have an anatomical connections of the brain, but you might be interested in learning functional connectivities. So there is not really a real graph in that sense, but you are interested in learning it. Or also in social interaction. You might know that two people are friends because you see them often together, but you cannot be sure. But so there are some examples, let's say, in which you are interested to learn the structure of the network. And the thing is that you can measure data on top of this network. For instance, you can have brain imaging, let's say, tools, or measure signals on top of these networks. So in every entity of the network you measure. And so basically this problem is like that we want to solve is to actually learn the topology of the network from the available data, okay? I will mainly use like the notation that we have seen before in the previous talk. So there is a ball vector X that will denote our graph signal, meaning every entry of that node indicates the value at a specific node. So it is a scalar value in general. And with the matrix S, I will denote the graph shift operator. That is this matrix capturing the relationship between the different entries of like the connections, okay? It can be the adjacency matrix or the Laplacian. So this is just an abstraction. Now, what is the problem of topology inference? So in general, we assume for now that the graph is unknown, but it's fixed, like it doesn't change over time, okay? And overall, what happens is that there is a latent graph and it generates some data that are visible to us under some process that we don't know. But in a way, we assume that somehow the graph, the data, let's say, depends somehow on the structure of the graph. For instance, the value at this node can be influenced only by the neighboring nodes and not by the others, okay? And this will be included in this F. And the problem of topology inference is to the inverse problem. From X, learn the G or the S. It is the same, so the graph shift operator. Okay. So there is a vast literature because this is an old problem. It started mainly from a statistical point of view under the lenses of the hypothesis testing. And lately it has been, let's say, also studied in the graph signal processing literature and also machine learning. It is a different approach, but let's say there are many works on this, and these are interesting, let's say, surveys that I would suggest if you are interested in it. So now, as I say, there are many models. Like, so what is the problem? That this problem we cannot solve as it is, in the sense that we need to make assumptions on this F. And in signal processing, this is what we do. We assume that the data that we observe, they obey to some particular generative model that we parameterize with some parameters, and we usually are interested in learning these parameters. In our case, we are interested in learning the graph, so the matrix S. So somehow this F should be parameterized by the S, and we want to learn. Now, there are many problems. I will consider only three models, so three different assumptions, because in our work we also consider this, but there are multiple. And I will also use this as an example to give you a concrete example of what kind of assumptions you can make about the data. So if you assume, for instance, that every signal that you have is generated from a multivariate, let's say, Gaussian distribution with a mean and a covariance, essentially there is, under the lens of graphical models, you can essentially estimate conditional independence between different entries by learning the inverse of the covariance matrix, that is called a precision matrix, and it boils down to this problem. So if you solve this problem, where our S in this case corresponds to the precision matrix, so the inverse of the covariance matrix, you are learning conditional independence between variables. And this, if you assume that the X are generated in that way. If you instead assume that every entry at a particular node is like a linear combination of the neighboring nodes, this goes under the, and this is a sort of neighborhood regression. So you just aggregate the values of the nodes, the adjacent nodes. And this is called a structural equation model. In general, the structural equation model might also consider inputs that are outside of the graph, so exogenous variables. But we don't do it for simplicity. And as we have seen before, we can measure smoothness on top of a graph. So the signal variability, we can assume that our signal is not high variable on top of the graph, and it is captured by this quadratic form. So under this hypothesis, if we assume that our graph is, let's say that our signals are smooth on the graph, we can learn our matrix S, that in this case represents the Laplacian, by solving this problem, where essentially we are saying learn the graph such that the signals that I have are as smooth as possible on this graph. So this will give us a graph, okay? However, sometimes this graph changes over time because, like, the graph, the graph changes over time, and also the data, we don't have all of them already, but maybe they are in a streaming fashion. So we would like to actually recursively, let's say, update our estimation of the graph, and without waiting for all the batch of data. So the scenario is the following. In general, let's say we have like a graph that, as you can see, some edges appear, some other edges disappear, and we can measure some signal on top of the nodes. The number of nodes remain the same, so there are no new nodes incoming, but the edges are changing, okay? And this is what happens, but what we get is the following, is we only get the signal on top of the graph, so we don't get like the node itself. So what is the standard approach for this problem? Well, you could say, let's say I wait all the data, I create windows of batch of data, and then I learn for every batch of data, I use one of the algorithms before to learn a different graph. So suppose that these are EEG data, I solve a problem, I get a solution. So for every batch of data, I learn different graphs. So these are my solutions over time. I could potentially also learn the whole problem at once by constraining these solutions to be like close together, if I want that they are not too different from each other. However, this problem is a bit computationally expensive because you are solving a lot of problems that the dimensionality might be high. Also, it is not really real time. So if let's say you are interested in a real time algorithm, this might not be the best solution. And also you need to know where to window. So you need to know where is like that the graph maybe doesn't change too much. So you need to know this. So in this sense, we have worked on this in the past. And basically what we created was an abstraction. So from all the models that we have seen so far, we created an abstraction that captures all these different models. So we can analyze, let's say, theoretically, the abstraction, and then you instantiate a model, and then you can create error bounds for that particular model. But the overall idea was to actually abstract all these different learning problems, and then analyze it, and also like making operating in non-stationary environments. So if there is like the data changes over time, also like statistically, you can make it work. And it is also accelerated. I will explain all these things. So I will explain what I mean by all of this. All right. So essentially, if we assume that at every time instant we get a new signal, what we have is that we get a function that is one of the models that we've seen before, like the 3D squares that we have seen before, is changing because at every time instant we get a new data. So the least square problem, we will have our matrix X collecting all our graph signals to be bigger. So basically our F is changing, okay, over time. So the index T is an index, it's not like a parameter itself. So we have a time varying function where our F capture the data fidelity, so in that sense, like the least square, the fitness of the model, and the regularization and the constraint that we want our graph to obey goes into the G. So basically, what we would like to solve would be to solve for every time instant this problem here. And this will be the similar way of doing a window, basically, in the previous case with one sample. So every time we have one sample and we solve the problem. However, this is clearly, this would be like a worse problem than before if you want for a real-time solution, or if you want, like, it wouldn't be, let's say, the solution in that sense. And for the 3 examples that I showed before, this is what they would look like, the F and the G. And in particular, I have rewritten, let's say, this function in explicitly as a function of the covariance matrix sigma t. Because before there was, for instance, in the other 2, there was the X, there was a matrix X, but you can rewrite them as a function of the covariance matrix. And the reason why I rewrote in terms of the covariance matrix is because we can basically decide how to update it. So what I mean is that we can recursively update the covariance matrix with, for instance, an exponential moving average. And we can discard all their data through this sigma, or weighting more the older data according to what we believe is happening. So if we think like that the data somehow statistically they are maintaining the same statistical statistical properties, we can give a big gamma, otherwise we can discard it. Okay. So now I say we don't want to solve it from like this problem because like as it is, because it might be expensive. So the way we did it was through a prediction correction scheme that is built on an iterative routine. I'm going to explain what I mean. So when I say a prediction correction scheme, it means the following. So at time t, what we do is we basically create a prediction of what the next function at time t+1 will look like. And the way we do this is basically through a Taylor expansion of the function f. We do a Taylor expansion towards the time dimension. So not towards like our variable, but towards the time dimension. And if there are questions on this, I can come on that later, but just think that we basically look at where the function is going. And I'm also using a vector here, okay? Because our matrix is symmetric, so we can just use the lower part of the matrix in general, and it is easier for gradient computation and dashouts and everything. So this is the prediction. And at time t+1, a new data arrives. So what we will do is then to actually solve the real function, that is basically that one. Now, it seems that now we have 2 problems, so then we didn't gain much because we didn't want to solve that as it is because it might be expensive for every time instance, and now we have 2. So the way we do it is that the prediction, we would like to solve this approximation, but what we actually do is to do an iteration, some iterations of a descent operator. You can think it as gradient descent, maybe constrained, but a sort of gradient descent on this function. So maybe we do 2 prediction steps, one like for one, okay? And then we get like that will be like the predicted next solution, okay, at time t+1. Then what we do here is the same. When the new data arrives, we get the function, and we do again some descent on the new function by initializing our variable with the predicted one of the step before. So essentially, we do few steps of a descent operator. And basically, if the graph doesn't change too fast, we hope that we converge to actually. So we want that our iterations over time will be faster than the velocity in which the graph is changed. Essentially, this is the overall idea. So in this way, we have light computation in the sense that we don't need to solve exactly the problem. We can just do a step of gradient descent, so it's quite fast. We have like that the instantiarity is somehow tackled with the exponential moving average of the covariance, and it is also accelerated. Now, clearly, let's say, if we solve this problem exactly with a solver, and for instance, CVX is a MATLAB solver, or it's a solver also in Python. We cannot do better than this. But what we can do is to actually converge to it, because that's what we want. We basically propose a trade-off between velocity and accuracy of the solution. So if you have a lot of time, you can do a lot of descent steps here, so you will converge to this. But we want to see how far are we from this. So that's what we can compare with. So these are, for instance, there are more examples, let's say, in the full article, but here I just show you what happens. So for instance, here we have a piecewise constant graph that will change at this point. And essentially we see that the method that we use is the predicted, like the one that we do through the iterations, and the optimal solution that we will get with the offline solver, like with CVX. And we see that, like, over time, we convert, let's say, to the batch solution, to the CVX solution. Then when the graph changes, we will depart from it, but then we will come back, let's say, again to that. And then here I also report, like, what are, like, the average time, like, in our case, to compute, let's say, the solution for each time instant, and what is the one that CVX will take. So here there is a good balance, a good trade-off between the velocity and, because we can learn the graph like with the same somehow, with the same accuracy. So like we can get the same solution after a while, but we spend way less for everything. Then we also did like some example on real data, but that's not our goal. Like in terms of, we don't want to make some let's say, real study on and give conclusions, medical advice. No, we want just to test our algorithms on real data. So in this case was a seizure data set. So basically there was a recording before a seizure, the pre-ictal interval, and after the seizure, the ictal interval. So we learned the graph over all these recordings. And these are two snapshots of the graph that has been learned before the seizures and after the seizure. I mean, there is some difference. We cannot say why or what this means, but we can just display what the graph is, and we also color the nodes with different centrality indices, in this case, the betweenness centrality. And then without, let's say, with the tool that we use, we can also see, for instance, every edge of the graph, how it changes over time. So this is like a feature that might be useful to see, okay, every edge maybe disappears, then it appears, and so on. And also, like, what is the difference between two adjacent solutions during the iteration. So, let's say our main contribution was theoretical. So, and with this, I think we reach the conclusions, and I hope that you have a better idea of what it means to learn a graph from data and why you want to do that, possible applications, and so on. Thank you.